Hey, trig enthusiasts, we're looking at Law of Sines and the Law of Cosines today. The British call them the Cosine Rule and the Sine Rule. The Americans call them Law of Sines, Law of Cosines. Doesn't matter to me how you want to refer to it. I'm going to derive both of them for you. I think it's an interesting and worthwhile pursuit. I think it'll help you remember them and understand them better. But if you're not interested, go ahead and fast forward me until you see the Law of Sines and Law of Cosines and apply them from there. But if you are a method enthusiast and ready for a little fight, check this piece out with me. If we're trying to solve the triangle, when you solve, you find all the angles and all the sides, right? You could say 180 and subtract these, and you'd get 40 or something like that for this. And then to try to solve the triangle using SL2U3, you'd have to find these sides, x and y, whatever they're called. The problem with this is none of these are right angles, so we can't use right triangle trig, right? SL2U3, sine, cosine, tangent only work for right triangles, and this is not. So we can't play that game. We have to do something else. We could do something like this. We could perhaps break this up into pieces. If we dropped an altitude from here to here, we could break this up into pieces and find all the bits. So that might look like this. Same triangle. I dropped an altitude. You could use the 22 to find the height. You could use the height to find x. You could use both of those values to find these sides. Might look like this. Right? You'd say sine of 40 is h over 22. You could solve for h. Fine, looks about right. And then you use h to find x. We know that this is approximately 14. And so you'd say now sine of 30 is opposite over hypotenuse. No problem. You could also use those to then find this and this separately, and then you'd add them together, right? No big deal. That's great. It works with this triangle, but I don't want to have to do this every time, right? I want an equation that I can just throw things in and crunch the numbers, put it in a program in my calculator, and that's where the cosine rule comes from. So this is the derivation of the cosine rule, and in the end we should get this: c squared equals a squared plus b squared. It looks a lot like Pythagorean theorem, right? There's c squared equals a squared plus b squared, and then we also have this piece tacked on to the end. Where does that piece come from? It comes from this derivation, which I think is interesting enough to spend time showing you. But you got to roll with me a little bit on this. Here's our triangle, our non-right triangle. If we drop a height, and this is too small, sorry, let's call this length E, and let's call this length F, just for clarity. We know that we could pick a right triangle out of this, right? Call this right triangle and say c squared equals e squared plus h squared. Fine, right? So I want to find e and h in terms of other variables like c, b, and a. So I know that e, this value e is really the whole length b, right, minus this f length, right? So like this whole value and then back up f. So it's b, and here's minus f, right? So e, the short length, is really b minus f. I wish I could point to the screen and have you see it. All right, so that's great. This is just an expression for e, right, in terms of other pieces. I want to do this. I want to separately talk about this height here, right? I know that the sine of c, this value, is really opposite over hypotenuse, h over a, and we know that the cosine of c is adjacent over hypotenuse, right? So we have those two values. We're going to mess with them, right? I'm going to solve for h and solve for f. And what's nice about that is now we have some values. Oh, why isn't that going away? We have some values that function for h, but that are in terms of a and c, a value for f that are in terms of a and c. And that's great because now we can plug those in and sort of combine terms and get rid of, I don't want to talk about E and F and H. I want to only talk about A, B, and C, and we can put those together like this. E was B minus F. But now we have a new value for F, which is A cosine of C. So instead of B minus F, we have B minus A cosine C. Okay, fine. So we're going to take that and crunch it into here. So here's my value for H, right? It's this piece. That's this, right? So A sine of C, H is squared, so H is squared. And then here's E, right? We have a new name for E here, and we substituted in, we like B, but we substituted in this F value. So we put this into this F, and then we put all of that into E. And so this is E. All right. If you square the red stuff, you just get sine squared C and sine and A squared, right? It's like 3x squared. You get 3 squared and x squared. So that's this piece. This is the red bit. This is a binomial, and if you expand it, it looks like this. And it's pretty awful, but here's B squared. Here's A squared cosine C squared. And then when you multiply them, you get 2 of their products. Okay, so this is just this piece. And this is the rest of it. All right. Great, that's nice. What's neat about that is that these last pieces look really similar. And if you factor out an A squared, right, you can make the sound effects if you like, you end up with this. There's A squared times cosine squared C plus sine squared C, right? And then you have the rest of the stuff there, the rest of the leftovers. There's the B squared and the other piece. What's neat about cosine squared C and sine squared C is that it always equals 1. There's a proof back here, but if you just think about the unit circle, if you take sine squared, sorry, sine is the vertical and cosine squared, you always get 1 because 1 is the radius of the unit circle. It's A squared plus B squared gives you C squared, and this is always equal to 1. You could also think about it in these terms where you're talking about ratios of cosine of C is adjacent over hypotenuse squared, the H over hypotenuse squared, and you can clean them up really when you get F squared and H squared, right? That is A squared, and you get A squared over A squared is 1. That's sort of a more formulaic way to look at it. Either way, this cosine squared C and sine squared C is 1, so you get 1 times A squared, and all of this mess left over. If you rearrange it and you put the A and the B together, you get this, which is a little more recognizable as Pythagorean theorem, and then minus this bit at the end. So it's basically Pythagorean theorem with a tweak that makes it work for non-right triangles, non-RTs, non-right triangles. Cool. That's the law of cosines. So looks like this. Get out of here. There's a law of cosines. One thing to notice about that is it doesn't matter what you call the angles, but this side, C, should be, it is the angle across, is the side across from angle C, right? This one's capital, these are lowercase. This is a side, C, B, sorry, A, B, A, B. They're all lowercase because they're sides. Uppercase, capital, it denotes an angle. So the order of A and B doesn't matter at all. But angle C has to be across from side C. So if we try it here, we want to find the length of BC, right? This, since it's across from angle A, we could call it length BC, or we can also call it side A, right? Those are synonymous. It's across from angle A, so it's side A. So if you throw it into the cosine rule, you'd say this side C, which we don't know, should equal the two other sides squared minus 2 times those sides times the cosine of the angle across from the side we're looking for. When you crunch those numbers, this is BC squared, so you have to crunch those numbers and then take the square root, and you should get like 8.8. Cool. Cosine rule. Super helpful. If you want to try it again, try AB. Here's AB and here's C. Try to find all the rest of the measurements, which just means find length C and measure of the angle A. Pause me and I'll show you some solutions in a second. All right. So I trust you're somewhat comfortable with the cosine rule, but if you're looking for side C, right, side C, you'd have to say C squared equals A squared plus B squared minus 2AB cosine of the angle across from this. The angle across from that should be C, 32.2. Make sure your calculator's in degrees, and be careful how you put things in. I usually put this in, and then I put this in, and then I multiply these, and then I subtract these two pieces. You should get, you take the square root of that 112-ish. Cool. All right, so there's one tool trick up your sleeve. Here's another one, which is the sine rule. Works with different applications, and that's this. Sometimes the cosine rule is just is too much. There's always a relationship that you can use that's a little bit easier to work with, and that's the sine rule, or the law of sines. So I'm going to show you where it comes from, but it just comes from the idea that the sine and sines, cosines, tangents are just ratios. So if you're talking about the sine of A, it's the opposite over the hypotenuse. Great. If you're looking at sine of B, it's just opposite over hypotenuse. They share that H. So if you solve for H, it looks like this. Oh, switch colors. Sorry, man. H should be B sine A, and H should be A sine B. H is the same thing, right? H is just this length. So really, you can say this H and this H are the same. So you can equate these two things, right? And you get B sine A is A sine B. They should be the same thing. This is really what the law of sines says, but we can make it into a more memorable pattern by moving the B's and A's to the other side, right? Divide this side, but divide both sides by B, divide both sides by A, and you get something that's a little easier to digest, which is this. The sine of the angle over its opposite side should equal the sine of any other angle divided by its opposite side. So, for example, you'd say, all right, well, the sine of this angle, theta, so you'd say, all right, sine of theta over its opposite side, in this case is A, right, over A. That should be the same ratio as the sine of any other angle. Let's use C because it's fun, right? Let's call it phi. I like phi. Should be equal to the sine of phi over its opposite side, which is, in this case, C, right? So you'd have to know 3 out of the 4 variables and then be able to solve it. Let me give you an example. So here's the law of sines. Doesn't matter what you call A and B as long as you're consistent. Yeah, let's get rid of that. We want to find angle C. So here's angle C right there. Let's call it theta. And so we can use this relationship and say, hey, the sine of theta divided by 11, but divided by its opposite side, should be the same ratio as the sine of any other angle in the triangle divided by its respective opposite side, that side. So divided by 8.8. All right, so then if you multiply 11 to both sides, you get sine of theta equals 11 sine of 42 over 8.8. And when you do that, my calculator's in degrees because this is in degrees. So you should say 11 times sine of 42 over 8.8. And then I get 0.836, blah, blah, blah. Right? That doesn't look like a very good angle, and it's because it's not an angle. It's the sine of the angle. So to find the actual angle, right, this is still sine of theta. So to find the theta, take the inverse sine, and I get 56.7 degrees, which seems reasonable for that. Cool. All right. If you want to try it again, give it a shot here. Find Q and R. Here are the answers. All right. One last tricky bit. Sometimes in the sine rule, there's two similar triangles that could be created with these angles. Let me give you an idea. And it depends. It doesn't always happen. It depends on which angles you have and which sides are given. So it's called the ambiguous case, and it can occur when the smaller of the two angles, or the two sides given, is opposite that given angle. So it happens when this is the only angle I have, and the smallest of the two given sides is across from it, right? So that's the case in which you can make two different triangles, one of which is this. This length, 8, always has to be this long. I can't change it. This always has to be 20. I can't change it. And this length has to be 6. I can't change it. What we can change, we can mess with this angle, we can mess with this angle, and we can mess with this length, right? They didn't tell us anything about that. And so therefore, with this same parameters, 20-degree angle here, 8, 6, we can take this thing and flip it over, slide it over. I haven't violated anything, right? This is still length 6, this is still 8, this is still 20, but I've made a separate triangle, right? If you don't include this piece, right? We've made another triangle that works with these parameters. So let's try it out with this case, and let's find one of these angles, right? Let's find this angle here. Let's call it theta. So you'd say, all right, well, sine of theta over 8 over its opposite side should be the same as sine of 20 over its opposite side, 6. Crunch a little numbers, so you'd say 8 sine of 20 all over 6, and take the inverse sine of that, and I got theta should be, let's call it 27. Great. So there, theta is 27. This can the same value can happen if you flip this 180 degrees like that, and you squeeze it over in here, right? This angle is still going to be 27, right? Just like this angle. If you work this out geometrically, you might have to just take my word for it at this point. And this angle, because this is a line, this angle phi is going to be 180 minus 27. Cool, so 180 minus that, 153. So that's our other angle. Okay, there's two possible ways to do this. Let's look at another piece. So here's another example of the ambiguous case, where you get a triangle, and you get the angle that's required is opposite the smaller of the two sides. that tells us that we're going to have a ambiguous case triangle. We can say we can find the sine of find C using law of sines. You say sine of this over this equals, what are we trying to find? The angle B. We want to find the angle C, so we're trying to find this guy. All right, so equals sine angle C. I'm going to call it theta again, over its opposite side. We solve for C, and you get this, right? You get 41.6. Great. But because there's a second possible solution, this 7 could turn in a different way. Like this length could be a lot longer, and so this length can be changed. We can move this one way or the other. I might have to show you a better geometric method for that. So we can take this length of 7 and just pivot it in a little bit, and this will be 41 and this will be 41, so this angle in here would be 180 minus the 41, so that's where this comes from. So ambiguous case is whenever you have that angle crossed from the smaller of the two sides. You're going to have to do this subtraction piece. Cool. Give that a shot. We'll work on them in class a little bit and get you squared away. Goodbye.